Hi, I'm Ryan. So we're from Comcast, and so for those of you who don't know, Comcast is the largest private internet provider in the world. But we're not just that. We also use machine learning in a lot of our processes. So we're part of the Comcast Applied Artificial Intelligence group. And that group has 4 primary projects. The first one is media and video analytics. We also have voice and NLP, and recommendations and search. I'll be talking about those 3 briefly, and then I'll turn it over where we'll talk about the crux of this presentation, which is our machine learning and data science piece. Comcast has the voice remote. And for those of you who don't know, it's either a physical remote that you have in your home, or you can even download an app on your phone, and you can talk into either of these interfaces. And what happens then is that your speech goes into the cloud where we transform it to text. And then we perform some natural language processing on that text to grab the intent out of it. And from that intent, we then perform an action resolution. So maybe that's showing you an asset page, or maybe it's tuning to a specific channel. And of course, then we delegate messages to the set-top box as necessary. Let's say, for example, you have the query, who plays the oracle in the matrix? What happens with this query? First, you ask it, and then it goes into our NLP modules. And then it returns back the action, which is either an ID or text. In this case, it's the asset page of the actress who plays the oracle in the matrix. So a lot of these queries can be superficial. There's a lot of metadata at the asset level itself, like genre, credits, synopsis keywords. All those things are fairly easy to query over. You know, if you say, show me all these sci-fi movies, it knows exactly what to do, and that's very simple. But we can actually go much deeper than that. There's much more data within the asset itself, such as chapters, moments, and annotations. If we think of a TV show or a movie, we can divide it down into scenes or parts, and then we can look across those scenes or parts and figure out things that are happening in those individual moments of the asset. Why is this useful? Well, from a customer perspective, let's say you have the question, what are the best moments on TV? Here, you're clearly not really looking for full shows or full movies. You're looking more for clips. And we're able to curate those. We're able to find those based on that query and show you them. Another really useful application of this is in-game highlight navigation. Let's say you have pre-recorded sports content. You're just curious about maybe your fantasy team, or for some reason you want to look at just the highlights of that sporting event. We have machine learning that can actually go through and find those highlights, find things when action is happening, find moments when you might be interested to watch, and you can navigate through them extremely easily on the X1 platform. Even contextual queries, like if you're watching a movie and you say, who's in this particular scene? You want to know the actors or actresses there, you can even do that. And then, of course, search and recommendations, always going to be important for some sort of content delivery platform. You're able to search for things you want, either by broad categories like sci-fi, or also just get recommendations based on what you like. For this personalization experience, we want the customer to have a relationship with their TV that goes beyond just watching. We want to say, what is popular right now? And then we combine it with, what do you as a user like? And when we do that, we can then create personalized recommendations that provide a more custom and personalized user experience. So that was a bit about the 3 other projects inside the Comcast Applied AI group. Now I'll hand it over to Bernard and Bhavana to talk about the machine learning and data science piece, where we look primarily at customer service operations, trying to improve the customer experience.
So I will talk about this avoidable track hole. So it's a very important problem that was actually mentioned by Professor Burg this morning. And what it is about is we're in charge of the whole delivery of the internet. It's not like the last little meters to your home. It's a whole infrastructure. And you might have very complex problems. So what we see is just the symptoms, but the root cause is the key problem. So if I follow exactly the way we see those kind of problems appearing is that first we get from our set-top boxes, we get a set of errors coming out. So we have the stream of the error coming out. It's kind of time series. And then later, maybe we have somebody calling us, and we have the customer care agent that will take a note and try to solve the issue. Of course, if the customer care agent can solve it, it's great. Sometimes it's a bit more complex than this, in which case then we have to roll a truck there. And that is, it's a bit problematic in the sense that people need to take time off to be at home. And needless to say that we have to put gas in the trucks, roll there, come back. It's at least half an hour operation for 30 seconds of work there. So we try to avoid this inconvenience to users. And putting the care agents on the spot, they get a call and say, hey, I see this, what is it, can you fix it? It's a bit tough on them because we are dealing with a very complex system. And Comcast is not doing internet, we have also cable, but we have also home security systems. We have IoT there, so there's many things going on. And humanly, it becomes a little bit mind-boggling to follow it and to make a diagnosis. And interestingly, it's empty in my little boxes there, which is not foreseen. But what is happening is that since we can collect all this data, we can put it together, there is an unfair advantage to machine learning because we can look in scores of data over the time and to make decisions for it, instead of having the customer care agents that go through all these kind of little debugging scenarios that are really painful to users because you go to one, hands you over to the other one, finds again, and it's so basic sometimes. So the idea there is just to use the machine learning and to leverage all the experience we have there to make a smart decision and possibly then to provide a better customer experience by solving at the first call, solving without asking embarrassing or always coming back questions, and possibly also to avoid to sending trucks out there. So now we're talking a little bit about what the problem really is, and I will go through what people normally never do is I will explain how we build a model, how we fail, how we get better, how we fail again, and then Bhavana will tell you how we go to greatness or better. So predicting this avoidable track roll, actually the question could be reformulated differently. The key question is the error that triggers the customer call, is it an error in the dwelling? Like a little rabbit who has been gnawing through the cable, which happens sometimes, or is it sometime up in the infrastructure, in which case probably it impacts hundreds of customers. And then in this case, we send an infrastructure track, which are different people, and they go in these boxes and so on. But if we don't know, we can send hundreds of tracks to each home. The guy arrives to the home, checks everything, takes half an hour, and finally says, I came out from nothing. And in addition, in this case, the guy will not say this really, and he will make customer care, help the user, and the feedback he gives us might not be really, there was nothing at home, we say customer education or whatever. And then we get some elements to learn on that might not be very accurately describing the situation. But that's real life. That's why we joined Comcast, is we want challenges. So there are many track rolls, yes, that are not solving the problem, and it's well known in the industry. I cannot give you numbers, but that's a big impact, and since the professor of Stanford mentioned it this morning, it's a big, big thing. And we want to go to the core of the problem because that's the only way we can improve in the long term. Otherwise, we will always be firefighting and sending these trucks out, and it's just not good. So we need a learning that can give us a root cause. So a kind of a black box. I don't want to mention which ones are black boxes. Is a bit difficult to use because if we can come back and say, here is this problem, the first question we get from our guys in the field, they say, why? It's good to have the solution, but explanation is equally important. So it's about exactly 1 year ago that we started to build this first model, and we're using two trails of information. The one is with the track roll, and the other is with network health. Of course, we are trying to measure out of the network to understand what's going on there. So I just follow the flow of the information here. So we get these customer calls in. We call them IVR, and then they are classified in buckets and so on. The care agent tries to solve them. If he can find a solution, it's solved there. If not, then we will send a track out there, and then the guy there has to solve it. So what we call avoidable is, in this particular case, is when the guy puts in his job description or the report, intermittent problem, I arrive there, it works, what can I say? No problem found, okay on arrival, and so on. So these are the ones where we could improve the experience of the user by solving them from elsewhere in the network. Second source of information is network health assessment. As you imagine, we have these network elements, and they are all IP enabled, and they want to give us a state of the network. So you can see it as a state space. These variables vary in time, so we have time series, and it's a bit like semantically what I show there. We have this time series coming in, and we try to make sense out of it by looking at a signature like this, if this signature can give us a state of the network. So classically, the learning phase is the following. We take these two streams of data in, the time series on the right side, the calls in the middle. We merge them together. And in the builder system, we have a reason code. That is why we think what is the cause according to the call agent. We feed this in the machine learning, then we send the track out. The guy gives us some codes of what he fixed there to fix the problem. So this makes then a supervised learning. And out of the machine learning, here we use gradient boosting most of the time. Then we can predict if the track roll was avoidable or not. A bit late here. Of course, in production, we will predict it before we roll the track out. And the first results we get were not good, at the least. Okay, but let's comment on the goodness of H2 on this. I can see, when I see something like this, I say, that's not good. I look at the ROC curves. They are too flat. I know that my model is not good. Accuracy 0.67%. I will certainly not get the pay raise on this one, rather a kick in the butt. And we see also that it's not really converging. So that's the self-critique. Yeah, we could do better. But guess what? This is the most important model for me, because given this model, now I go to the experts and I tell them, hey guys, I know nothing about networks. I'm a bit not so smart. That's what I got out of your models. What do you think about it? So I could start a discussion with those guys. And those guys came back with two suggestions. So one say, what about the network topology? Did you take care of it? And I'm like, maybe not. And the second one is, you are not looking at the good real-time information. What can you do there? Okay. So it took me 1 week to build this second model. And I had to think a little bit about what the expert told me, and I could build a model in my head. Extremely simple. Here, I'm just going, since I knew from each household how I could go up in the network, I could rebuild a little network topology. I looked in my learning sample, and I made a kind of average or a vote on each network. And obviously, if on each network node everything is green, like the track roll was not avoidable, well, that's good for me. But if the track rolls were avoidable, and I have red ones coming in, all of a sudden, I can have questions about was the node of this health good or not? Despite the measurements that I get that tell me it's good, I don't trust them. And then I have a feedback that is of interest here. Using this first feedback, I had to making it a little bit weaker as data scientist because I had all the predictions over the whole period of time, and I had to remove the ones that we had not seen yet and so on. So I did something like this here, still in simulation mode. And I ran my model again. And now it's like, wow. So now I show this to my boss, and now he says, hey, now it's too good, you know. What did you do? There's something wrong with you. I look at it and say, yeah, this is not too good. We have something to do something there. But my boss is right in the sense that, you know, since I did kind of doctor the model a little bit, but the learning out of it is the truth is in the network. I might not have had the good measurements from my network guys, but I know that if I go there, I have 93% accuracy. That's the way to follow. And again, small, simple graphics that I always praise from H2O, for me, they work. I understand them. It's a good thing. The other thing I understand moderately is that by looking just at the importance of a variables, I don't want to go through description of them here, but I put all this effort in making my time series. It's always tedious time series. I think we are missing a dimension there. But when I look here, what they are giving me compared to the trouble they are giving me by putting them together, I said, not worth it. Let's drop the time series. You know, there's no return of investment on those guys. And also, since my expert was saying we should look at the new network features that we had not on the time, it was time to build a new model and now get it right. And to get it right, I will ask Bhavana to tell you how she did.
Thanks, Bernard. So third model was different from the first two models. What did we do different in the third model? So firstly, we wanted to understand the flow that Comcast was following. So to understand the call center flow, we spoke with the domain experts, and from them we got to know this information that when the customer, when he encounters an issue, when he calls the customer center, what happens? So the first thing that happens is that the customer service agent goes through something called interactive troubleshooting guide. So this guide is a sequence of actions and responses that they have to talk to the customer to find out the reason for which they are calling today. So the end or the child nodes of the tree is the reason code for which the customer calls the call center. So once the reason code is determined, then the issue can be resolved on site, or the issue needs to be looked upon by the domain experts. So there are two ways from here. So considering the issue is not resolved and the call center agent failed to resolve this issue, then we raise something called as the trouble call. So trouble call is nothing but a trouble call ticket which is created by the call center agent. Now when the agent creates this ticket, she or he assigns the zip code, the dwelling. The dwelling is an enumeration which can either be residential for the residents or it can be commercial for industry businesses. So we have two types of dwelling, and the customer service agent will also get the zip code from the customer who's calling, and also the reason code which is determined from the ITG. So they consider all of these three information and they assign the ticket to the biller system. Now what happens in the biller system is, the biller system is a system which runs every night, which goes through the open tickets, that is the trouble call, and the job creates something called a job type. So the job type is determined by the zip code, by the dwelling type, and by the reason CD, which was determined by ITG. Now all three information together creates a job type. Now once the job type is generated, the technician visits the customer premise and then determines what's the resolution, and the turnaround time can generally be 1 to 3 days. Now we wanted to automate this process, so what did we do? So for the automation of the process, we deployed a machine learning model. What happens in the machine learning model is that we identify the signals which are very important for us. What are the important signals? Firstly, it is the reason code that we determined from ITG. The second important signal is the ticket information, the zip code information, and also the dwelling type information. Now, having all of these information and using the historical data of how the technician solved this issue, what did he use to solve this issue, what was the completion code for the issue to be resolved. We collect all of this information and couple them with the network health data, which we get from the watchtower. What is this network health data? Network health data is the topology of the nodes. Every customer premise is connected to a node. A node can be upstream or downstream. That is, the problem can originate upstream or the problem can originate downstream. So all of this information is available in network watchtower. So that is national watchtower. So once we get the on-track data, which is the trouble call data, we couple that data with the watchtower data. So now we have the joint information and also the historical information of what was the resolution, right? That we used it as the supervised learning model. That is the label, the target label for the supervised learning model. Now all of this information is fed to the supervised learning machine learning model. Now once this information is fed, the target is if the truck roll could have been avoided or not based on the completion or based on the reason code. So this was our learning phase. Now what happens in the prediction phase? In the prediction phase, we don't have the information of if the ticket was avoidable or not. So the machine learning model should generate this information. So for this inference again, we used on-track data and coupled it with the watchtower data. And then we gave the result that if it can be avoided, yes or no. It's a binary classification in the end. So this was our third model. And the accuracy that we reached using the H2O tool was 93%, and also the log loss error was converging very well for the training and the validation. The ROC curve reached a threshold of 0.5, which was optimal, and the accuracy was again 93%. This was pretty good, but what was lacking in this model? Then what this was during the learning phase, but then we had to deploy this model and then find out the results. So what did we do for the deployment? We did some simulations, and the simulation, this is the data from the simulation. The green graph indicates that we were correctly identifying the avoidable truck roll, and the orange indicates that we failed to identify, and gray area is something that the data couldn't have been collected or some misclassified data or the data not being available, that is the missing data information. So having this data, we reached an accuracy of 90%. So during the real time also, our results were in sync with what we achieved during the training phase. So this was pretty good. So what was the disadvantage of this model was only one factor, that we were predicting preventing the truck roll only after the customer calls the call center. Now what could have been done better? That is, we want to predict the truck roll before the customer even calls the call center. That is, we want to preemptively solve all the issues. So currently the team is working on preemptively solving this issue, and what they are using is something called reinforcement learning paradigm, where they feed the issue and then the machine learning model predicts the outcome. You learn from the outcome and then again you improve the model. So we are getting into the era of reinforcement learning. This is where we are right now, and that's all we have today. Any questions?
All right, we got some time for questions. Let's check the Slido, see if there's anything there. And we can always do this the old-fashioned way for folks that want to ask a question in the crowd. Just feel free to raise your hand. Okay, the gentleman here. Let me go down and pass this mic to you.
Yeah, good idea.
I'm K.R.S. Murthy. I happen to have major inventions in Comcast type of cable before the Comcast existed in GE. The telemetry data that you get from the device, in addition to the customer calling and so on, how much of sensory data do you have on what's happening, what are the faults that come back to the head end and that you can collect now this cloud and so on? What are you doing in that? That will be, in fact, that will be large before the customer calls. Customer even realizes there is a problem. Mm-hmm. And as long as you have all of that in your telemetry, and you can also use telecommand to go back and correct if you could correct anything, or design the set-top device itself which can do that, or any other device that you have. So
Okay.
You guys are hot.
Ah, yeah, we're hot. We are exactly working with this telemetry data nowadays. It's still challenging. because this telemetry data, if you compare it to classic data series where you have samplings that is very consistent and so on, we cannot use the theories that you use currently in control systems because of the sampling rates that are far distant from this data. But we collect gigabytes of data. We have lots and lots of data, and we are working now in narrowing it down to find out what are the good assets to look at and not. But it's a very nonlinear problem, I would say, very complex problem.
We did it on General Electric before any of this tabletop set-top converters were there. It depends on how you design the whole set-top converter. What is the telemetry commands that go back, or a telecommand you to enable. You are already enabling remote, saying, this you can watch this extra feed for you and all of that. So it's a matter of how you design, and also doing the thermal analysis will be very important in terms of failures.
Yeah, but we are not designing the box. I mean, in theory, yeah, it's all feasible to do. Yeah.
The problem is yours.
Oh yeah, the problem is ours. It's a big problem.
So we've got some questions from Slido. You can take a look at the monitors and see if you want to answer them.
How did you deploy H2 model? Who wants to answer this?
Sure. So H2O, as I'm sure you all know, provides plain old Java objects, and we were able to take those and wrap them up, build a wrapper around them, and then deploy them as a REST service. And then we simply queried the REST API with a record, and that would give us a prediction back, which was really helpful for the deployment team to just be able to give them these POJOs, which they could swap in and out of the wrapper fairly easily.
We go to the next one. How we are using reinforcement learning. So we're at the very beginning of it, we have to say. So we have to find some actionable items in the network so that we can use the reinforcement learning, so that we can change some parameters and see how it interacts on the whole network. So it's work in progress. And as said, we don't have a mathematical model. It's not as simple as deploying a model somewhere where you know the mathematical model of the thing. So we have to deploy it and we have to make tests. But it's kind of dangerous because it could be also disruptive for the whole operations. How do we combine time series? Time series are a big problem for us. I believe something is missing currently in time series. The representation is just a little bit tricky at the moment to do in machine learning. So how we do, we slice it in time and we give different labels. I'm not happy with it. It proved to work in the past, but we have been using some deep learning networks also, which hides, I mean, it's just hiding the problem of the time series. The time series are more or less implicitly there. Time series are problematic. I have no secret weapon for this one yet.
All right, let's give our Comcast Silicon Valley team another hand.